Namaskar friends. Welcome to MedDwise Circle Educational Video Lecture Series. In this video lecture series, we are going to discuss the fundamentals of clinical chemistry test in a pathology lab. This is intended to be viewed by freshly newcomers in IVD industry who have recently completed their education, or maybe experienced people who are working in IVD industry for a few years and want to refresh the basics again, or maybe our laboratory technician brothers and sisters who are doing the pathology test themselves. This video lecture series is made in collaboration with Anamol Laboratories Private Limited. So allow me to share my screen. Friends, I hope you all can see my video. As I told you, we have different modules to understand the fundamentals of clinical chemistry. In this module number 1, we are going to discuss about the basics of photometry, in which we will discuss what is wavelength, what is complementary color, what is Beer Lambert's law, what are the components of colorimeter, and what is the difference between colorimeter and spectrophotometer. But in our previous video, we have already discussed the basics of wavelength and complementary color. In this video, we are going to discuss what exactly is Beer Lambert's law and how we use Beer Lambert's law in our day-to-day life in IVD industry. So without wasting time, let's go and understand the basics of photometry. Before we start the Beer Lambert's law, today's lecture, we will first, in 1 minute or 2 minutes, we will quickly recap what we understood in our previous lecture. In the previous lecture, we understood what is light, how light travels from point A to point B in the form of wave, and what is the meaning of wavelength. We also understood that light, the wavelength is measured in terms of nanometers, and it is denoted or signified by the letter lambda. Basis on which we understood what is ultraviolet spectrum of light, what is visible spectrum of light, and what is infrared spectrum of light, and how visible spectrum wavelength of light has 7 different colors. We also understood what is the meaning of complementary color, where what is the color of the reaction mixture will determine which wavelength of light we have to pass through the solution so that we measure its absorbance. We also understood the concept of absorbance maxima and absorbance optima, where absorbance maxima is the wavelength of light which shows maximum absorbance, and absorbance optima is the wavelength of light which only shows the absorbance of the target analyte and nullifies the absorbance of any kind of interfering substance. Now, we understood the concept that whenever the solution is colored and we pass light through that solution, the colored solution will absorb the light. But how much light it will absorb and how it is helpful in our IVD industry? To understand this, we have to understand the concept of Beer Lambert's law. So let's deep dive into what exactly is Beer Lambert's law. Friends, we understood that hypothetically, for example, if this is the colored solution and we pass light through this colored solution, there are only 4 things, or maybe more than that, 1 or 2 things more than that, which will happen to the light. Imagine this gray is the colored solution, the reaction mixture, and the orange lines are the light which we pass through the solution. In the first case, when the light hits the colored solution, it will again go back in the same medium from which it came, which means that if this is the colored solution and light came from this direction, it will hit the colored solution and it will again turn back and go in the same direction or in the same plane. This concept is called as reflection. There is a second concept where light will enter into the colored solution and some amount of light will pass through the colored solution and enter into second plane. This concept is called as transmission. There is a third concept where the light will enter into the colored solution and the solution will absorb the light. This concept is called as absorption. There is a fourth concept where the light will enter into the colored solution, pass through it, but change the direction. This is called as scattering. This concept is called as scattering. So whenever we pass the light through the colored solution, one of these four things is likely to happen. This concept is slightly more discussed in this particular image. Just imagine we have a light source, and through the light source, the light goes through something called as a prism, and it goes through something called as a wavelength selector. This wavelength selector will allow a particular wavelength of light to pass through it and fall on the colored solution. This colored solution will absorb some amount of light, and the balance amount of light it will allow to pass through it, which is transmitted light. The transmitted light will fall on something called as the detector. And the detector will ultimately tell us how much light was absorbed by the color solution. So we are here interested only in the concept of absorption and transmission. Absorption means the light it enters on the colored solution and the solution absorbs the light. It does not allow the light to go away from the solution. So how much light will be absorbed by the color solution? This depends on primarily two things, which is the color intensity, and it is also known as the optical density. So as I told you, there are two things which determine how much light will be absorbed by the color solution. The one thing which is responsible for absorption is analyte concentration, and the second thing is light path length. Let us try to understand this one by one. Now, say for example, I want to estimate the amount of glucose in patient sample. What will I do? I will take a clean test tube, and in the test tube, I will add the glucose reagent. In this glucose reagent, I will add the patient sample, which is serum, human serum. And the human serum, along with the reagent, will do the reaction, and it will change the color, or it will form a new color. This color intensity depends on how much glucose was present in the human serum. If the human serum had very less amount of glucose, the color will be light. But if the patient sample had very high amount of glucose, the high concentration of glucose, then the color which will be formed will be very, very dark. So if the color formed by the reaction mixture is very dark, it will absorb more light. But if the colored form by the reaction mixture, the solution is very light in color, obviously it will absorb less amount of light. So absorbance of light really depends upon the concentration of the analyte what we want to estimate. In this example, the color of the solution the intensity of the color depends upon the concentration of glucose in the human sample. There is also one more thing that determines how much light will be absorbed. This thing is called as path length, which means that light will enter from this direction and it will exit from this direction. So what is the length of the test tube with which the light is still in contact with the solution? This thing is called as path length. So if the entry point and the exit point, the distance is very large. That means the light is for a longer period of time, it is in contact with the solution. Therefore, the solution will absorb more light. But if the test tube is very narrow, the entry point and the exit point is very close to each other. That means the light is for a very less period of time in contact with the colored solution. Therefore, colored solution will not have more time to absorb the light. Hence, the absorbance of light depends on two things. Number one, it will depend on the concentration of the analyte, which we want to estimate. And secondly, it will depend on the path length. Now, concentration of analyte is directly proportional to light absorbance. This concept was given by a scientist called Beer. And the path length of light is also directly proportional to its absorbance. This concept was given by a scientist called Lambert. So hence, in Beer Lambert's law, it is always important to note that we have to take both these factors into consideration. So absorbance of light is directly proportional to the concentration of the analyte and the path length. Now, in most cases, the path length is uniformly set at 1 centimeter. Therefore, we say that absorbance is only directly proportional to concentration of analyte because the path length is fixed at 1 centimeter. So this does not change. 1 centimeter is the distance between entry point and exit point of the light. So hence we avoid whatever is the variation by path length, by fixing the path length. So the formula for Beer-Lambert's law is as follows. Absorbance is equal to molar absorption coefficient into concentration of analyte into path length. A is equal to epsilon into C into L. Let us understand one by one. A means absorbance, how much light is being absorbed by the solution. C means concentration of the analyte. And L is the path length. So in earlier, we understood that absorbance is directly proportional to concentration and path length, which means if the concentration will increase or the path length will increase, the absorbance of light will also increase. The relationship is directly proportional to each other. So when we want to remove the directly proportional from the formula, and replace it by is equal to, we have to add a coefficient, a constant in the reaction. This constant is nothing but molar absorption coefficient. We will not go into the details of molar absorption coefficient, but let us understand that this is a constant factor. So hence, this is the formula. Now, friends, tell me, if I directly add the patient sample in the glucose solution and the color is formed, and when I pass the light through this colored solution, will I come to know about the concentration of glucose in the patient sample? The answer is no. To understand this concept in detail, let me give you one example. Let's say hypothetically, I manufacture a weighing balance and I ask you to stand on the weighing balance and the weighing balance will tell your weight. Now, hypothetically, let's say the weighing balance will tell your weight as 500 kilograms. Now, you and me, both of us know that your weight or my weight is not 500 kilograms. How will you prove me wrong? You will only prove me wrong by introducing a known value weight. So when we know that the weight of this iron metal is 1 kilogram and I put it on the weighing balance and the weighing balance tells that the weight of this metal is 1 kilogram, then only I will become sure that the weight of my human body is, let's say, 80 gram or 80 kg or 90 kg or 100 kg. Therefore, we will not be able to identify the value of unknown sample until and unless we use a known value sample. This is the importance of a known value sample. Similar thing also happens for estimation of glucose. Hypothetically, I only have one test tube and in this one test tube, I add patient sample and it will form a color. How will I come to know that this color means XYZ concentration of glucose? I will not come to know until and unless I also run one more test tube along with this, which has a known value. Let's say this test tube is for a standard. So when I add a standard and I know the value of standard as 100 milligram per deciliter value or concentration of glucose, and it will show a particular intensity of color, and I will absorb the wavelength. I will absorb the OD. I will take the absorbance or optical density. And when I compare this optical density with the patient sample, then only I will come to know what is the concentration of glucose. This is how we use Beer Lambert's law in our day-to-day life. So Beer Lambert's law is a formula to use to identify the concentration of unknown values. This is the formula that we very frequently use for Beer Lambert's law. Concentration of unknown value divided by concentration of standard. In this case, standard is a known value, is equal to optical density of unknown value divided by optical density of standard. Now, we have three things which are already known to us after doing the test. When we perform the test, we run two different test tubes. One test tube is for standard and one test tube is for patient sample. For the first test tube of standard, we already know the concentration, which is hypothetically 100 milligram percent. We take its absorbance. Let's say the absorbance came to 0.25. Then we take the second test tube and we do the reaction in the same way we have done the test for standard. Now the new absorbance is 0.5 for patient sample. So here in this formula, what we will do is we will just put the values over here. Concentration of unknown divided by 100 is equal to 0.5 divided by 0.25. So therefore, concentration of unknown is equal to absorbance of unknown multiplied by either concentration of standard, it will go here or on the opposite side of the is equal to sign. So when it goes to the opposite side, it will change its position from denominator to numerator. So OD of unknown multiplied by concentration of standard. Then again here the OD of standard. So this is the formula for identifying the concentration of unknown value from Beer Lambert's law. Now let us try to understand this equation more in detail. Concentration of unknown is equal to absorbance of unknown multiplied by concentration of standard divided by absorbance of standard. Now let us focus on this particular part, which is concentration of standard divided by OD or absorbance of standard. Now friends, I would like to ask you a question. Let's say we have a standard of glucose of the value 100 mg per cent. Now, whenever I run the standard, which means I will take the reagent and I will add the standard in the reagent, and the standard will form a color. This reaction mixture will form a color and I will note the absorbance by passing light through it. Now, if I get the value of the absorbance as 0.25, will this value change over a period of time? In other words, I would like to ask you that if I run the standard on Monday, the value will come 0.25. On Tuesday, will the value be different? Let's say in January, the value is 0.25 of the standard. In March, will the value be different? Obviously, no, right? So whenever a standard of a fixed value of 100 milligram percent is run, always the absorbance that we should get is 0.25 only. Which means that if 100 milligram percent is fixed, then 0.25 absorbance is also fixed. In other words, both these things are constant. So one constant divided by second constant will always give us third constant. This constant is in our scientific language, we call this constant as something called as factor. So factor is nothing but the formula for a factor is concentration of the known value divided by the absorbance of known value. This formula is often used in our IVD industry, where the new formula for Beer Lambert's law now is the concentration of unknown sample is equal to the absorbance of unknown sample multiplied by the factor. So whenever the factor changes, the concentration of the unknown value also changes. This concept is very heavily used in our IVD industry to find the concentration of unknown value, which means we have to find the concentration of patient sample. We will not be able to find the concentration of patient sample until and unless we have either the factor or we have a known value sample inside the kit, which is nothing but either a standard or a calibrator. Both standard and calibrator are known value samples. Friends, I hope this video has been helpful for you. And through this video, you understood the concept of Beer-Lambert's law and how we apply Beer-Lambert's law in our IVD industry to find out the value of unknown samples. If you have any questions or suggestions, please write down in the comment section. It will help us to improve our future lecture series. And please spread this video with all of your friends. Thank you very much, friends, and I will see you in the next video.